So in this video, we're going to talk a little more about dependent events and how the multiplication rule works for them. So to start off with, let's look at this example here. In a bag of 50 Skittles, 10 are green and the other 40 are actual good flavors. The probability that it's a green one would obviously be 10 out of 50. But let's say we pick 2 Skittles randomly. What's the probability that they're both green? Or if I pick a Skittle, put it back, and then pick another Skittle, what's the probability they're both green? This right here highlights the difference between independent and dependent events. This option here is independent because the first pick is not going to influence the second pick because you put it back and you mix them around. So these are independent events, whereas these are not. These are dependent events because the second pick actually depends on, that's why it's called dependent, it depends on your first pick because you took one out and that affects the numbers. So let's talk about this. For this one with independent events, you just multiply the probabilities together. So the first pick being a green would be 10 out of 50. The second pick being a green would be 10 out of 50. And you just multiply those two probabilities, and that's how you calculate with the multiplication rule. With dependent events, it's very similar. You just have to adjust, like after the first pick, you have to adjust the probabilities based on what you picked. So for example, the first Skittle being green would still be 10 out of 50, but now I've taken a green out. And so I'm only left with 9 greens left out of 49 total Skittles left. And so they're very similar, you still just multiply, but I have to adjust that second one based on what the first outcome was. So this rule looks like this, and really I would just use common sense more than anything, but the rule looks like this. For dependent events, to find the probability of event A and B happening, you still just multiply them together. The probability of A happening times the probability of B, but we call this the probability of B given A. Basically what this means is it's the probability that B happens given that A already happened. Like A happened, so it's the probability of B given that A. Sometimes this is written as B given A, so if you ever see just like a line like this, it means given. So for example, 2 cards are drawn without replacement from a standard deck of cards. If you want to become a card counter, I don't know. Find the probability that both cards are red. So the probability that the first card is red would be 1/2, or because half the deck is red, half is black. So you could just do 1/2, or there are 52, so there's 26 red cards out of 52 total. Now the probability that the next card is red, because you're not going to put your first card back. So the probability that the next card is red, you only have 25 red cards left out of 51 total cards. Basically just bump it all down by 1. And so if you multiply those together, let's see what we get. Alright, so as a decimal, it's 0.245 approximately. So about 24-25%. Alright, so here's another example. An aquarium has 6 male goldfish and 4 female goldfish. You randomly select a fish from the tank. Do not replace it, which means they're going to be dependent. And then you pick another fish. What's the probability that both fish are male? So you've got 6 male out of 10 total. The probability that the next one is male would be 5 out of 9, because you only have 5 males left and 9 fish total. Alright, now let's do the probability you get a male and then you get a female. This is the same thing, but the numbers will adjust slightly. So the first one being male would still be 6 out of 10. Then what's the probability that I get a female? So there would actually still be 4 females left because I haven't taken a female out. But there would be 9 total because I took a male out on my first pick. So this would be the probability of a male and then a female. Last one, imagine you have 15 mochi balls in the freezer. Love a good mochi ball. 5 are mint, 7 are chocolate, 3 are tangerine. You randomly pick 4 of the mochi balls. What is the probability they are all the same type? This is actually slightly trickier than it might sound. All the same sounds easy enough, but what this is basically saying is, what's the probability that you pick 4 mints in a row? Or, and since it's an or we're going to add, what's the probability that you get 4 chocolate in a row? Or, what's the probability that you get 4 tangerine in a row? So either of these scenarios, we could have all the same type. And so it's basically, it could be this, or it could be this, or it could be this, and so we add them together. You may be noticing this can't happen. We only have 3 tangerine, so the probability that we're gonna get 4 is 0. So we don't have to worry about that one really. We're just gonna have to add up these 2. Let's start with the mint. What's the probability that we just reach in and randomly pull out a mint? That would be 5 options out of, how many total are there? You've got 15. So that's your first pick is a mint. If the second pick is a mint, that would be 4 out of 14. Third pick would be 3 out of 13, and then 2 out of 12. So that would be your first is a mint, second is a mint, third is a mint, 4 is a mint. All right, we'll add that to the chocolate. So basically the same thing, just with the chocolates. So we've got 7 out of 15. Then if we have taken a chocolate out, now we'll have 6 out of 14, then 5 out of 13, and then 4 out of 12. So when you multiply all of that together, I'm just gonna leave it. You guys can handle the calculator, but if you put all that in your calculator, you would get your answer. I think that's it.